let's look at the completion times for both of these schedules. So the schedules are at the top, and we're going to say what's the cost of sigma star. That's just equal to the cost of, well, everything that came before, plus the cost of everything that came after, plus the cost of the two jobs, job J and job I. Similarly, for the sigma cost, it's the cost of everything before and after, plus the job cost of I and J. The only real interesting thing that I'm denoting here is that I'm saying that the total running time of everything that comes before, so the sum of durations from everything that comes before, is TB. So TB is just equal to the sum of everything that comes before, the durations of everything that comes before. And that shows up in a few places. So that's the only piece of notation that should sort of be unusual for this slide. Otherwise, we're just saying PJ has a completion time of whatever the duration of everything that comes before plus DJ, and PI has a completion time of everything that came before plus job J plus job I. And then similar for sigma. So what we want to show is this. The cost of sigma star is less than the cost of sigma. If that turns out to be untrue, that's a contradiction, which means that sigma star cannot have been optimal, and the greedy schedule has to be optimal. All right, so let's compare these two equations. I'll put, and I'm really just being lazy here by putting cost before, because we can notice that's the same for both schedules, so that makes it easy to cancel out. So I can really just immediately cancel out the costs from before and the costs that after, because those don't change between the two schedules. So that leaves me with, on the left-hand side, this part of the equation, and on the right-hand side, this part of the equation. If I distribute through, on the left-hand side I have this, and on the right-hand side I have this. And I'd encourage you, if you want to dig into it, just to pause the video and verify that my algebra here is correct. Well, there are several terms that can be canceled out, and I'll highlight all the terms that can be canceled out in orange. And what you notice is all I have remaining is PI times DJ plus PJ times DI. Well, we can compare those two terms. And a good question to start with is, which side is actually bigger? So you can ignore this inequality because we're going to use that as part of our contradiction. I want you to think about it and say which side is actually bigger. This is a little tricky to look at in this form, but how about I rearrange the equation a little bit? So let's divide both sides by DI and by DJ. So that doesn't change the inequality. I'm just dividing both sides by the same amount. And what that'll do is it'll cancel out the DJs on this side and the DIs on this side. And what I'll end up with is that equation. So PI DI is less than PJ DJ. Well, that is our contradiction. We know that since the greedy schedule says that I should come before J, that the ratio of PI DI has to be greater than the ratio of PJ DJ. So what this really means is that this inequality is false, which means that the optimal schedule is actually the greedy schedule. All right, so one thing we haven't handled in this set of slides is what happens if we have multiple reorderings. So for example, this is I and J here. Well, you know, they're more than one apart, so how do we do that exchange? Well, it turns out if you have things that are multiple apart, that there have to be some swaps in the middle as well. So we can handle that by first doing a swap between those two, and then doing a swap between those two, and each time our schedule gets better. So really just doing multiple reorderings or having a sigma star that's even more out of order just sort of results in us having to do more of the exact same argument over and over again. All right, well, let me just give you a chance to look at this. So if you want to, you can pause this video, but essentially what it is it's just running through this exact same process and showing you the difference for even just 6 jobs. We can get a difference of sort of 175 compared to 387 with randomly generated data. So it can make a pretty big impact on a pretty efficient algorithm. All right, so our summary of this greedy scheduling algorithm is that if you're given n jobs with a priority and duration, and each job has a score based on the ratio, then if we schedule jobs in decreasing order of their score, then we will have an optimal schedule. One interesting question I think you should think about, and feel free to discuss on Slack or ask me questions during office hours, is what should we do if we're given more jobs while these are running? So we have N jobs. Let's say we run 20 of those N jobs, and then we get another M jobs. What should we do under those circumstances?